Okay, so this will be the final video in the Let's Get Started in Lyra series. This will draw to conclusion chapter 10 with our persistent inventory. For future videos, we'll start a new playlist and continue to add capabilities to Lyra and explore different Lyra capabilities. But for this final video, what I thought I'd do is walk through the final state and the final C++ for the inventory manager, as that's where most of the inventory persistent logic resides. So first, sort of how it stands. As I log into my persistent session, open up an individual game, and launch into a world. Upon loading the world, you'll note that my abilities in the bottom right-hand corner are already set from where I last left off. If I press my L key or my skill tree, you'll see that my skill tree is where I left it off. So each of the skills that I had set up on the last session are still active in this session. My abilities that have been granted and have been slotted into the due slots. And my inventory is as I left it, be it resources or crafting recipes or building components. And finally, anything in the storage is still in the storage. So all of that is supported by the inventory manager and tying it to the persistent layer. So let's take a look at that C++ code. So what I thought we'll do is walk through the header file and then walk through the C++ file to kind of just give everyone perspective on where we ended up after bug fixes and testing to make sure everything was functioning appropriately. So if you remember, we defined our structs that were the send data to. So this is the definition of the data we were sending to the persistent layer in the form of the actual data elements and then just an array of items inside that. And the data elements we needed to receive data from the persistent layer and set up the game. So those structs are just defined for sending to and receiving from the database layer. We inherited our inventory manager from the Lyra inventory manager. So we made no changes to the Lyra inventory manager. We simply subclassed it and then added capabilities on top of that. We have a small function here that is really only for testing in maps. So because of the with editor, it will not get packaged into the final game, but it allows us to log into a map, connect to the persistent database without having to do the login window every time. Then we have our functions used to retrieve the data from the persistent layer. This is by far the most complicated process, and we'll try to talk through that a bit more when we look at the C++ code, but know that pulling data from the database server and setting up your game is far more complicated than pushing data to the database server. So these are the functions that are responsible for pulling data off of the database server. Conversely, there's only one function to push data to the database server. So we end up calling this function quite frequently every time we pick up an item, craft something, etc. These functions are all called on startup only. Then we have a series of helper files, really just determining whether we should show something in the inventory, whether we should persist something into the database, are we only allowed to pick up one of these, such as a recipe or a building blueprint, and then our get active user session and character. Of our private variables, these are all just variables used in the process. Some functions here that help us in the startup activity. So how do we get the primary asset ID from an item instance? And the reverse of that, how do we take a primary asset ID and return a item definition class? So those two are just helper functions for there. We created two functions to activate the skills. So basically it simulates what happens when you click on the activate skill button in the UI. So when we load, we actually activate those skills through the exact same code, just simulating someone pushing the button. Same with activating the related abilities. And then we had to create a refund skill point function that maybe we should add a switch to activating the skills or creating a separate gameplay ability to activate it without taking the points away. But what we found is that the simplest answer was to refund the player all the skill points and then immediately take them away when we activate the skills. So we'll see that as we go through the code. Then we have our basic server connect, which is what connects the game instance to the inventory manager as we join a session. The API calls for getting data from the OWS2 API structures. And then the rest of this is just straight API calls through the OWS structure. All right, so looking at the C++ file, the first thing we did is define a couple of static tags. These are the tags you should recognize from the other chapters. These are the tags that we need to interact with in order to pull our data out of the inventory manager and then ultimately store it in the database or pull it back out. We turn the component to not tick. We do replicate it. We're only replicating two variables, the active user session and the active selected character. We pull from the configuration files, the INI files, our various settings for the API calls. So these just pull out of the INI files the corresponding values. Here's our replication of our two variables between the server and the client. And then on begin play. So here's where some of the complexity starts to materialize. So the first thing we do is we cache our player controller just for performance basis and just check whether or not that was successful. Then we test, is this the owning client? So if we're in the component of which the player controller is locally controlled, then this is the owning client, and therefore we can call our game instance and get our session connection setting here. Conversely, we check if we are on the server, and both can be true. If I'm hosting a game, I am both locally controlled for myself and I'm authoritative for everyone else joining my session. But think of those as two separate things. If I am the server and I have authority, then we simply fire off two timer events that are looping. The first one loops and checks to make sure that the asset manager is fully loaded, and that's looping every half a second. The second one kicks off and determines whether or not we've received the data we need from the database, and that's looping every 1 second. So immediately upon begin play, we start these two delegates on a timer, and we just have them looping, waiting for their conditions to be met, and in which case then we'll continue processing once both conditions are met. So it's a good way on begin play to fire off these events or functions, not knowing exactly when they're going to end, but knowing that the conditions have to be true before we continue processing. So we have two, the check asset manager is loaded, and the process persistent inventory. So we'll come back to those in a second. This function is the server connect to the persistent database. This is where we call from the owning client and pass it the login. This block of code right here is only for testing purposes. So it's only if we log into a map, spin up this inventory component, and we don't have a connection to a game instance, then we wouldn't have an active user session GUID. Therefore, we're going to make an attempt. So we set the component to listen for the UI event login successful. So we listen for this event, and then we trigger off the game instance this auto login process, which will complete by sending us this event. And so because we've set the listener to this event to be our login message received, that's the delegate function that will get called when the login is complete. So this is, again, all just for testing. If we're not with the editor, we don't do any of that stuff. We simply go get the persistent inventory, or we call for the persistent inventory. Here's the on login received. That's the part of the testing only logic that blocked with the with editor begin and end. And then here's where we make our request to the database to send us the data. So that will be called right here if we're not with editor, or here if we are with editor. So it just works through each of those. Or if we're in our testing scenario, when the login message is received, we then call it right here. So 3 places that could trigger a call to request persistent inventory. So 1 here, 2 here, 3 here. All of them end up here, and we make a request of the database to send us the information we need. When that request occurs, we wait for the callback. The callback comes back with a JSON object here, and then we parse that JSON object into our received data struct. So we take that JSON object, we parse it into this structure, and we determine whether it was successful. If it was successful, we let go of this latch. So this is one of the 2 latching mechanisms that is holding back processing. Remember, I said we needed to have 2 events occur. One was the data came back from the database. 2 was the asset manager was finished its initialization. So this is one of those 2. And then here we're checking the asset manager. So here was the second one, which determines, do we have an asset manager? If we do have an asset manager, has it finished its initial scan? If those 2 conditions are both true, we turn this latch off. If it's not true, we simply re-queue the timer with the exact same function. So this function gets re-queued again here if these don't pass. So if we did not load the asset, if this flag did not turn on true, then we simply loop back again one more time, wait another half second, and just continue looping here until both these conditions are true, in which case we can continue processing. Speaking of continuing processing, so here we basically are waiting to see if we have both the inventory from the database and the asset manager loaded. If both of those conditions are true, we'll continue, we'll perform this exercise. And if not, if they're not true and we're not yet ready, then we set the timer one more time and we loop for another second and then call ourselves again. So here we process persist inventory, which is the name of this function. So we queue one more timer and we wait again. If in the second wait, the inventory database has come back or the asset manager has loaded, if both conditions are true, we then go in to our code and continue processing our persistent inventory. Otherwise, we take another loop. All right, so let's assume that we got through all of that. We once again check to make sure we have the asset manager. We then load all the item definitions. Now, this is for debugging purposes. We're logging out in a verbose log all of the items in the asset manager. This was more just for debugging purposes, just to understand what the state of the asset manager was. And we basically go through and check all of that. The important part is here, where we check, is any given asset that we're looking for valid and loaded? So if it's not loaded, then we're going to go ahead and add it to this array. So we process through all the unloaded items and set them up in array so that we will later load all of those items. Now, performance-wise, we're probably going to change this, because if I have 5,000 items, I don't want to load all 5,000 items. What I really want to do is only load the items in the asset manager that I'm about to request from my player's inventory. So we're going to change this logic a little bit, but this was kind of getting us through the testing process and making sure things were working properly, which is you need to have an asset loaded before you can ask what its class is. And so we ran into a problem where if an asset wasn't loaded, we were getting a null pointer back when we were asking for its class. So the answer was to load all the assets, all the item assets, before making those requests. Again, we will switch this for performance reasons, and we'll only do this check for items that have come back from the database payload. But for now, we're doing all of them. So we loop through all the asset data that we got. So we did this asset type request, right? So we request any of the Lyra inventory item definitions from the asset manager. Here's where we make that actual request. It populates this asset data array, which is here. We then loop through that array, logging out the state of it just for debugging purposes, checking if it's loaded. If it's, not loaded, if it's not loaded, we add it to our array. And then assuming our array, if our array is empty, we just move on to the next step. We don't need to do anything. If our array is not empty, then we're going to create one more delegate, and we're going to not call finish persist inventory right away like we did here because our list was empty. Instead, we're going to pass that function as a delegate to the load assets. So what will happen here is whatever items are in this asset list, assuming there's something, because if it's empty, it's going to go here. Assuming there was something in that list, we will create this delegate function, which is identical to this function. We'll ask the asset manager to load the list of assets, which is this array, and then call the delegate, which is this function. So whether it's empty and we call it directly, or there's an asset to be loaded and we call it upon delegate, in both cases, we end up here to finish the loading of the persistent data. All right, we do, for debugging purposes, we do another log. All right, so we check the state of all the assets just to make sure that our asset manager did in fact load everything. This is purely a debug logic. It's got no function on the code at all. We take the JSON string that's in field value, and we convert that string into a structure. So here's our field value received struct. We take that JSON string that's in field value and we convert it. We then loop through every item in that struct. And for every item that came back from the database, we have to perform a number of actions. The first thing we do is we get the item definition from the asset manager. This is why we had to load those items so that when we called this function right here, it would not come back with a null. So if the item was not loaded, when we call this function, it comes back with a null pointer. That's the reason we're loading from the asset manager before asking it for the class. So we grab the class. The class allows us to add a brand new item instance. So here we add an item instance via the item definition, which is the class we got here. Now we have a brand new inventory item instance and all the default values and the fragments that are associated with that. We then check if the stack count in the JSON file was greater than 1, then we will add the stack counts -1 because there's already 1 when this got added. So we add our inventory stack counts here. We check which storage unit we're in. If it's 0, we do nothing, but if it's something other than 0, we'll add that many stack counts to get it up to where it needs to be. The skill activated status. So if the skill was active, we set the tag back to being active here. However, we do not actually execute the activation at this point. And the reason for that is we're somewhere in the middle of a loop, and further down in this loop, there may be some abilities that skill granted us. If we processed right here at this point, if we processed all the skills at this point, we could end up adding another ability into the inventory system, and we don't want that. So we basically postpone that and simply activate this skill at this point, but not actually process what it means to be active. So at this moment, the item has activated checkmark yes. However, the skill itself has not yet been activated. We then check the ability slot tag to make sure that the ability slot tag is not blank. The reason we use greater than 10 is our tag is longer than 10. And there's a scenario where we might have the word none. So when you convert a tag that's invalid, the answer becomes none. And therefore, sometimes in the database, it might write the word none. And therefore, none is less than 10. So this is a safer way to test that the tag actually includes kind of this string in it. We then request a gameplay tag converting that string into a gameplay tag, and then we activate the ability for that tag. So we'll see that in a minute. Now, once we're through the entire for loop, so this is the end of the for loop that we've gone through every item in the JSON file and added it to the inventory instance. Now it's safe for us to go back through that file and activate any skills that are necessary. So we then loop through all the items that have been added, looking for skill fragments here. If we have a skill fragment and that skill is active, then we can now activate that related skill. We do another logout for debugging purposes where we just list out all the inventory items. Again, this is purely for debugging. And that's the end of loading data from the database into an active session. So all of that we just talked through, all of that logic, all of those delegates are to deal with startup of a new session and populating your inventory, your skills, and your abilities appropriately. In contrast to that, this next routine is what we do when we write data to the database. So whenever we're making a change, we call update persistent inventory. That grabs the inventory items in a loop. We determine whether we should persist this item. So we have a flag. So some items like the pistol, the rifle, the health pack, we don't want to store those in the database. So those are set to off, but the other items we do. So we first check that. That allows us to skip the block. We then convert we get the primary asset ID, which is in the form of type : name. So it's the Lyra inventory item definition : ID _ whatever the case may be. And we make that a string and store that in the database. We then determine if we have any tags. We get the tag entry and convert that into this stack count, which is an int field. This working structure is basically this, right? It has the, It has the item class as a string. It has the stack count as an int, in storage as an int, skill activated as an int, and then ability slot tag as a string. So we're just populating each of those entries by checking the corresponding tags. Here we grab the fragment to get the slot. And then if we get to the bottom of all of that, we add that to our array here in our packaged inventory. Once we've done all of the items in that for loop, we simply convert the ustruct into a JSON object string. So we take this entire ustruct and create this resulting string, call our API, passing it the resulting string, and that's it. It's fire and forget. We don't worry about it. The only other functions that are probably worth a few seconds are when we get our item primary asset ID. So in this case, we're getting our asset manager. We're asking it for a primary asset ID for a particular object. So we pass the item definition T subclass into that routine, and it should pass us back a primary asset ID. We check that it's a valid. In other words, it's not blank. If it is blank, we do an error. Otherwise, we return it. This is the reverse. In the reverse case, we get past a primary asset ID and we need to return the class. So we do that here. We do the asset manager check. Here we get the primary asset ID object class, and then return that or issue an error if we got an error. Our should show items, should persist items simply are casting our, we're taking whatever item instance we were given and we determine whether it should show. So we basically grab the item instance, get its item definition. Off the item definition, we have to create a default object because this is just a class. And then that default object will populate with these values so we can then pass back one of these values. All right, the last two, activating the related skill. So in activating the related skill, we are basically sending the gameplay event to active. So we're using the same function that we do in the UI by triggering the send gameplay event to an actor. In our case, it's the player state, I believe. We pass it a specific tag, which was one of those constant tags that we defined at the top, and the activate payload. And so the activate payload includes the item instance and the number of points. So here we determine the points, we refund the points. That's where I said, look, we're going to go ahead and refund the points so that when we call this routine and take those points away, we have sufficient points to do that. So that's all there is to activate a skill. This will then trigger the gameplay ability associated with this tag, which Does all the same thing as if we were doing it on the UI. On the ability, very similar. We take our tag, we get our payload, and we send a gameplay event to the actor, though this time to activate an ability. So these two are very similar in that their net result is to send that gameplay event to the actor, which will then trigger the corresponding gameplay ability and do whatever it would have done when we did it in the UI. It's probably not worth digging through. This is how we refund the skill points. And that's pretty much it. So that's kind of the end of the logic around the persistent inventory management. Thanks for watching all these chapters in this series. It was a learning curve for us to actually put one of these together. What we'll likely do is move into some various other Lyra topics, probably around a character, selecting a character or modular characters, or some of those aspects. So once again, thanks for watching. Hopefully you found this informative. Best of luck. Thanks.